Hi everyone. So today we're gonna do another higher order linear homogeneous ODEs, but today we're gonna add some initial value conditions to the higher order linear homogeneous ODEs. It's gonna be similar like the previous lecture, but it's gonna require more steps to solve this, but it's not gonna be that hard. So without further ado, let's go to our first example for today. Hey everyone! So this is our example for today's higher order homogeneous linear ODEs with initial value conditions. So we have here an ODE with the highest order of 3. So our very first step is that we want to find its general solution and then applying the initial value conditions to the general solution to obtain the particular solution, which you will know how to do it in the next steps. So we want to do the same exact steps like what we did with our previous lecture of higher order homogeneous linear ODEs without the initial value conditions, which is taking the characteristic polynomial of this ODE, r cubed plus r minus, actually this is r squared minus 8r minus 12 equals to 0. And then from here on, we want to factorize this characteristic polynomial equation. But to do this, we cannot factorize this normally, so let's use another Horner's method, which we want to check for every value or every factor of 12, which could be plus or minus 1, plus or minus 2, 2 times 6, plus or minus 3, 3 times 4, plus or minus 4, 4 times 3, plus or minus 6, 6 times 2, and lastly is plus or minus 12, 12 times 1. So first, let's try and check if r minus 1, if r equals to minus 1 is a factor. So let's plug in minus 1 to our characteristic polynomial here, or negative 1. R cubed or negative 1 cubed is just negative 1, plus 5 times negative 1 squared is just plus 5, minus 8 times negative 1 is just plus 8, and then this minus 12 equals to 0, and let's see if this is equals to 0 or r equals to negative 1 is a solution. So we know that negative 1 plus 13 minus 12 equals to 0, and yes, this is 0 equals to 0, so r equals to negative 1 is a solution or is a factor. So let's write this down. R plus 1 is a factor. And then let's divide our characteristic polynomial with our obtained factor, which is r plus 1, or r equals to negative 1, by using the Horner's method. And so this is 1, this 5, this negative 8, this is negative 12. And keep in mind, this is going to be a long step because we have the initial value condition and we need to use our obtained solutions and apply it to our general solution to get the particular solution for this problem. So this negative 1, don't forget the plus sign here. Let's drop down the 1 and then multiply 1 here by negative 1. We get negative 1, 5 plus negative 1 is just 4. We multiply 4 here by another negative 1. So it's just negative 4. This is negative 12. Multiplied again by a factor. So this is just 12, this 0. And if we get 0 in the remainder, that means we've done our Horner's method correctly. So our new characteristic polynomial will just be r squared plus 4r minus 12. And don't forget to multiply everything here by r plus 1 equals to 0. And then, what are we going to do next? We're going to try and factorize our characteristic polynomial with the highest order of 2 here, or our squared characteristic polynomial. And to do that, we know that r squared plus 4r minus 12 equals to 0 is just r plus 6, r minus 2. So let's just write that down in the sake of the time. R plus 1, r plus 6, r minus 2, r plus 1, and everything here is equal to 0. And then afterwards, we know that we have 3 roots for this general solution of the corresponding ODE, which gives us y equals to c1 e to the r1x plus c2 e to the r2x plus c3 e to the r3x, and this will just equals to c1 e to the negative 6x, or let's just write it from negative 1, so negative x plus c2 e to the negative 6x plus c3 e to the 2x. And so this is our general solution to this higher order ODE. But remember, the question is not asking for its general solution because an initial condition is provided at the top of the question. So we need to find its particular solution. And how would we do that? Let's apply what we have here to our general solution. So let's write down our initial value condition again. Y 0 equals to the derivative of y 0 is equals to 0. And then our third initial condition is the second derivative of y of 0 is equals to 1. And then let's put a sign here so we don't forget, because we want to use our general solution in the end to obtain the particular solution for this ODE question. So first, let's find what's y 0 equals to 0 here for our first initial condition. So we have here our general solution previously was y equals to c1 e to the negative x plus c2 e to the negative 6x plus c3 e to the 2x, and then everything here is actually equals to 0. And don't forget that all of the x's are also 0. So we know for a fact that e to the 0 is just 1. So everything here is just c1 multiplied by 1 plus c2 multiplied by 1 plus c3 multiplied by another 1. So it is just c1 plus c2 plus c3 equals to 1. And so this is our first expression. Let's mark this down for our first initial value condition. And for our second one is the derivative of y of 0 is equals to 0. And so we need to get the derivative of our general solution. Remember, our general solution is right here. So the derivative of c1 e to the negative x is just e negative c1 e to the negative x. c2 times e to the negative 6x here is just negative 6 c2 e to the negative 6x. And lastly, our c3 is just going to be plus 2 c3 e to the 2x. And then from here on, let's apply our conditions, or let's put our values inside this derivative equation, which negative c1 e to the 0 is just 1, so let's not write that down. Minus 6 times c2, another e to the 0 is just 1 again, and then plus 2 times c3 e to the 0 is just another 1, so everything is going to be equals to 0 according to the initial condition. So this is our second expression corresponding our second initial condition to this problem. So let's work on the third one. So our third one is going to be the second derivative of y of 0 is equals to 1. So we got the first derivative of our general solution, and let's use this first derivative to get the second derivative and then applying the values within it. So we know that the second derivative of y is equals to negative c1 e to the negative x here is just going to be c1 e to the negative x, and then negative 6 c2 e to the negative 6x is going to be plus 36 c2 e to the negative x, and then lastly 2 times c3 e to the 2x is just going to be plus 4 c3 e to the 2x here, and then applying the values within it. So let's plug in the zeros. C1 e to the 0 is just 1, so, and then 36 plus 36, C2 e to the 0 is just 1 again, plus 4, C3 times e to the 1 is, e to the 0 is just another 1. And so this is going to be our third expression for this third initial value condition. So after finding all of these three expressions for three of our initial value conditions, we want to find the unknowns, which are C1, C2, and C3 here. And how to do that? You can do it based on elimination and substitution, but it's going to take a while. And I have a faster way, which is using the Kramer's rule actually to find the unknowns for this. First of all, for the very first step, let's try and find the determinant of A. But what's A? What's the matrix A here? Okay, notice that C1 plus C2 plus C3 equals to 1, and then negative C1 minus 6C2 plus 2C3 equals to 0. Actually, this is equals to 0, sorry. And then our third equation is C1 plus 36C2 plus 4C3 equals to 1. Notice our linear system of linear equations right here. We can transform it in the form of a matrix which corresponds to the unknowns that we want to find, and also towards the right hand side, of course. So this is just 1, 1, 1. This negative 1, negative 6, 2, and this is just 1, 36, 4, and our unknowns are C1, C2, and C3, and our corresponding right hand side factor will just be 0, 0, 1. Okay, so this is our A, and this is going to be our unknowns here. So we're gonna try to find our C1, C2, and C3. So let's try and find the determinant of A. So the determinant of a matrix, of a 3 by 3 matrix, we can use a special method called the Sars Method, which is just -1, -1, -6, 2, 1, 36, 4, and the Sars Method applies right here, which we only take the first two columns and put it behind here, behind this matrix. And what are we going to do by putting the first two columns behind the matrix? We're going to multiply it. So the rule applies that every time we multiply from the top left hand side, to the bottom right, diagonally, like this, we're going to apply the positive sign to each of them. However, when we multiply from the top right-hand side to the bottom left, like this, we're going to put a negative sign on it for each entries. So you'll see what I mean in a bit. So 1, let's multiply it from the top left to the bottom right diagonally. So 1 multiplied by -6 multiplied by 4 here is going to be -24. And then 1 plus 1 times 2 times 1 is just 2. And then minus 1 plus 1 times -1 is -1. -1 times 36 is just -36. And then minus everything in bracket. And this is why I put the negative sign outside, because we want to put the negative sign for every time we multiply diagonally from the top right hand side to the bottom left. Okay, so 1 times -6 times 1 is just -6. And then 1 times 2 times 36 is just positive 72 plus 72. 1 times -1 times 4 is just -4. So what do we get here is -24 minus -36 is -60. So it is -58 because we add 2 to -60. And then -6 minus 4 is just -10 plus 72 is positive 62. Positive 62 times a negative, so this is just going to be minus 62. And we all know that this is just going to be minus 120. So our determinant of A is negative 120, okay? But the question here is, how do we get the C1, C2, C3, or the unknowns of this linear systems equations? So to get the unknowns, it's pretty simple. We want to find C1, and we set it to, okay? So our determinant of A goes into the denominator right here. What we want to do in the numerator is just, we want to swap the column that we're trying to find. For example, we're trying to find C1. However, C1 corresponds to the column 1 here. Why is that? Because remember, the matrix factor multiplication is that we want to multiply 1 with C1, 1 with C2, 1 with C3, and then -1 with C1, -6 with C2, 2 with C3, and 1 with C1, 36 with C2, 4 with C3. So do you all recognize the pattern? That 1, -1, and 1 right here correspond to C1 right here. Or in other words, we can write this down as 1, -1, and 1. Multiply everything by C1 here. So that's why 1, -1, and 1 corresponds to C1, 1, -6, and 36 correspond to C2, and so on. So we want to swap the column that we're trying to find with the right-hand side right here. And so let's make this longer. And so by swapping the columns, I mean that the first column is going to be 0, 0, 1. The second column is going to be the same, and the third column is going to be the same. And we want to find the determinant of that unknown by doing another Sars method, because this is another 3 by 3 matrix determinant. And don't forget, our determinant of A is -120. And you'll see why we want to find why we initialize our determinant of A before doing anything else. So -120. So using the same method, the Sars methods, let's put the first two columns behind here and do the multiplication. And so remember, 0 times -6 times 4 is 0, 1 times 2 times 1 is just 2. 0 plus 2. And then 1 times 0 times 36 is just 0. So minus. Let's multiply it diagonally from the top right to the bottom left now. 1 times negative 6 times 1 is negative 6. 0 times 2 times 36 is just 0. 1 times 0 times 4 is just another 0. So we get here, and 2 minus negative 6 is 8. 8 over negative 120. And we all know that 8 over negative 120 is just equals to negative 1 over 15. And let's keep this because this is going to be our C1 later in our particular solution. Or let's write this down bigger so you all can see. And so for our C2 now, we're going to do the same exact steps again. Determinant of A correspond to column C2. Let's swap it with the right-hand side factor. And then over determinant of A. And you see here why we would want to find the determinant of A, because each of our steps require us to know what's the determinant of A. If we don't do this before we do any other thing else, we're gonna need to, it will require us to do much more work to do this, to solve this equation. So doing the same exact steps again. 1, negative 1, and 1, our original column 1. And replacing our column 2 with our right-hand side is just 0, 0, 1. And our third column is just the original column, 1, 2, 4. So doing the Sars method again, putting the first two columns behind the matrix, and then divide everything by negative 120. And so let's do the Sars method. Let's multiply from the top left to the bottom right. So everything's going to be positive. 1 times 0 times 4 is 0. 0 times 2 times 1 is another 0. 1 times negative 1 times 1 is negative 1. So this is negative 1. 1 minus, multiply everything from the top right to the bottom left now. 1 times 0 times 1 is 0. 1 times 2 times 1 is 2. So this is plus 2. And then 0 times negative 1 times 4 is just another 0. And negative 1 minus 2 is just negative 3. So this is negative 3 over negative 120. And we all know that negative 3 over negative 120 is just 1 over 40. And so this is going to be our C2. And keep in mind, okay, so here where the tricks come. We got C1, C2. And remember, in our system of linear equations before, we have this one equation, C1 plus C2 plus C3 equals to 0. If you don't want to do another Sars method and then dividing it by the determinant, if you think that requires you a lot of work, we can just use this equation as an advantage for us because we've got our C1 and C2 already, so we just need to set C3 equals to negative C1 minus C2, and we will get our C3 from there on. So let's just do that for the sake of the time here. Negative C1 is just positive 15. Negative C2 is just minus 1 over 40. And this, let's first match the denominators. Let's multiply them. 15 times 40 is 600. Okay, so this is 40, this minus 15. And so 40 minus 15 is 25 over 600. And we know 25 divided by 600 is just 1 over 24. And this is going to be our C3 here. And so we've got our C1, C2, C3. We've solved all of our unknowns here. What are we going to do? We're just going to do our very last steps, which is plugging in all of the unknowns to our general solution, which we obtained at the start of the problem before. So y equals to c1 e to the x. We know c1 is negative 15. Negative 1 over 15, sorry. E to the negative x plus c2 times e to the negative 6x. c2 is 1 over 40. So this is just 1 over 40. E to the negative 6x. And then our last one is c3 times e to the 2x. c3 is 1 over 24. E to the 2x. And so this is our particular solution, or our final solution to this higher order ODE with initial value conditions. And remember, to do all of these steps, it is easily that you'll make a mistakes in solving the unknowns or doing the Horner's method, but be sure to check again before you continue or proceeding your steps ahead.